Hello everyone, welcome to the second video of week 13. So we would like to talk about what is error detection and what is Hamming code, the 7.4 Hamming code, the 7.4 Hamming code as a typical error detection code, And then you will have to finish quiz 3, based on this week's video. So you do have the 7.4 Hamming code problem in your quiz 3, and you do have parity check code problem in your quiz 3 as well. So what is error detection? So we have talked about error detection, error correction in the previous video. So the error correction code is only able to find out if there is an error or not. So the error correction code basically helps us to answer the yes/no question. So yes, no question. If there is an error or not. If there is an error or not. So there's different types of error detection code. Sorry, this should come. We should go here. So there's different types of error detection code. And we have introduced the parity check, which is the most popular error detection code. Most popular error detection code. Parity check code. So Hamming code is also an error detection code because any error correction code could detect the error. You have to be able to detect the error in order to correct the error. So Hamming code is considered to be both error detection code and error correction code. Hamming code is considered to be both error detection code and error correction code. So error correction code basically means we do not only detect the error. We do not only detect if there is an error or not. We can also find the location of the error. We can also find the location of the error. So if you know where the error is, then you can simply flip the bit to correct the error, right? So if we know where the error is, we should be able to correct it because there's only 0 and 1. If I know this bit is an error, then I can just flip that bit. So that's the basic concept of error detection code. And we would like to know one typical error detection code, which error correction code, which is called Hamming code. So the basic concept here is a little bit confusing. It's not easy to understand, but basically what it says, Hamming code is a useful detection correction code, error detection and correction of the error. This code uses multiple parity bits. So again, it is made based on parity check. So by adding multiple parity bits, we could secure original message. However, there's of course certain limits. So we would like to add a k bits, and the k here is the number of the parity bits. K here is the number of the parity bit, and the n here is the number of the information. The n here is the number of bits in the information. So then therefore you will have n bits as the original message, and the k bits as the extra parity bits. So the length of the total code word, will be the k plus n, because you have n bits message and the k bits parity check bits, right? So then the total number of the code word has k plus n bits. So it's pretty abstract to look at the concept, but we will look at the example and everything will make sense. So it follows the certain procedure to generate the parity bits. So of course, by default, we are actually using even parity, but you don't have to know how you determine the parity bit, because every different types of Hamming code, they follow different procedure, and you will have those procedure to use for any problem. I gave you the procedure of how the Hamming code is generated, and you just use that procedure to figure out if there is an error or not. So this kind of procedure is shared to public. So if two community, two different parties, they communicate with each other, and then they have to let each other know, well, are we using a Hamming code to secure the message, and what kind of Hamming code we're using to secure the message, right? So everybody should follow the same procedure to detect the error, to correct the error. So suppose I will skip this page. You don't have to worry, but let's look at the example, then everything will make sense. So suppose we have 4 bits. Suppose we have 4 bits B1. Suppose we have 4 bits original as the original information, So, and we would like to add 3 more bits. We would like to add 3 more bits to make as the parity check bits, So, and the overall message will have 7 bits, of course. The overall message will have 7 bits, of course. And this is called 7-4 Hamming code. This is called 7-4 Hamming code because you have 4 bits information and you have 3 more bits added as the parity bits. You have 3 more bits added as the parity bit. So then overall, we will have 4 plus 3, which is 7, and this is the length of the code word. So altogether, this is called a 7-4 Hamming bit, Hamming code, 7-4 Hamming code. So example. So the 7-bit Hamming code is generated following this procedure. So we have 3 added bits, and they're called the parity check. Suppose we call them P1, P2, P3. And the original message are called D1, D2, D3, D4, right? And all together we can call them B1 to B7. We could call them B1 to B7, from the least significant bit to the most significant bit. So B7 on the left-hand side, all the way down to B1 to the most least significant bit. And the first bit, the third bit, the first bit, the 1, 3, 4, 5. No, I should say B1. B4. So hope it's clear here. So B1, B3, and B4. B1, B3, B4 are actually generated by the original message. Remember, the original message is only B7, B6, B5, B2. B7, B6, B5, B2. So there are only 4 bits. Original message. So I think there is a mistake here. So that's why it looks so weird. So I will make sure correct this mistake from the tutorial, make it on the slide here, and then make sure correct that error. Hope you don't get confused by looking at that. So there are a mistake here. There's no such bit. So if you count, there are 8 together. There are 8 total. So it should be the 1 bit, 2 bit, the first bit, 2, the second bit, and the fourth bit, So the B1, B2, and B4 are actually the parity check bits. And those 3 bits are generated by the original 4-bit message. So the original 4-bit message is the B7, B6, B5, B3, B7, B6, B5, B3. Okay, so we generate 3 extra bits and we put them on a different location to form the 7-bit code word. So how can we generate the first and the second and the fourth bit? So the first bit is called P1, and this is actually B1. This is actually B2. This is actually B4. So the B1, B2 and B4, they're generated using the XOR of the original message. The XOR of the original message. So suppose we do the XOR of B3, B5, B7. B3, B5, B7. Remember, our original bit message is given as 1, 0, 0. And then this is B4, 0, B2, B1. So we're trying to figure out B1, B2, B4 using the original message 0, 1, 0, 0, 0, 1, 0, 0, 0, right? So the B1 is actually using B1, P1, which is B1, right? So the P1, you can call it P1, you can call it B1. It's the first parity bit, it's the first bit of the code word. So the first bit is actually generated by the XOR of this bit. So this one is generated by the XOR of B3, B5, B7. B3, B5, B7. Okay, so you're kind of like sampling every other bit, of the original, of the code word, sampling every other bit of the code word. And altogether, this will give you the XOR of this, and that will give me the result of B1. That'll give us the result of B1. So, and then it is 1. So we'll put a 1 here. And then how can we generate the second bit, which is B2? So the B2 is generated. By the XOR of B3, B6, B7. XOR of B3, B6, B7. So 6, 7 here. 6, 7 here. 3 here. Right? So the B2 is actually generated by the XOR of the 3, 6, and 7. 3, 6, and 7. And it is actually 1. So if you do 1 XOR with 0, then it is 1. So we will put a 1 here. And then the last bit we need to determine is called B4. So B4 is generated by the XOR of the last 3 bits. The XOR of the last 3 bits. So 5, 6, 7. And that is actually 1, 0, 0. So XOR of 1 and 0 and 0. So the answer is 1. So we'll put a 1 here. So then, of course, you can get 0, you can get 1, and then using this procedure, and we could generate the 3 extra bit, and altogether it will give us a 7-bit, and we call this 7-bit Hamming code. So the 7/4 Hamming code means originally we have 4 bits message, and we added 3 extra bits to secure the original 4 bits, and then this is altogether 7 bits, and we will send this code word to send this code word out. And then you may have the question, well, how the 3 bits here can secure the original 4 bits? So by following the procedure, the principle of the Hamming code, and for this particular example, so we added 3 bits, we added 3 extra bits, to secure the original message, and the final message will be 1001 011. 1001 011. 1001 011. So that's here. So the final message should be 1001 011. And then remember that if you send this to your friend, and all your friend know is, oh, this is a 7/4 Hamming code. And all your friend know is actually all your friend know is the original message. The original message should be the 765, should be the 765 and the 3 and the 3. And the other bits here are actually the parity check bits. The parity check bits, and that's all he knows. That's all he knows. But each bit can be wrong, right? So this is the message you send out. This is the message you send out. However, your friend could receive some other message. Your friend could receive some other message. For example, suppose what your friend received is 1001111. So that actually means what your friend received is 1001111. So that actually means there is a mistake on the third bit location. There is a mistake on the third bit location, right? So suppose that's the case, your friend of course does not know which bit is wrong, but this is the code your friend has received, right? So if the receiver received such code, and how can the receiver recover or detect the error? How can the receiver detect the error? So the receiver will basically follow the same principle we actually did, because we actually generated the parity check bit using the even parity principle. The even parity principle. So we actually guaranteed the parity for the bit location 1357. And we could guarantee the parity for the bit group 3672. And we could also guarantee the parity for the bit group 5674. So this is actually bit location 4567, and this is bit location 2367, and this is bit location 1357. And if you look at the bit location I write down here, so they actually follow certain principle. So if I list B7, B5, B4, B2, B1, and the 1357 is actually sampling 13135 7. Oh, I forgot the 6, that's why. So the 1357 is actually sampling the bit location, every other bit location. And the 2367, did I use blue? Yes, I should use blue. The 2367 is actually taking 23 here, 67 here. So every other two bits. And the 4567 is actually taking every other 4 bits. So you're sampling in different pattern. And you're trying to maintain the selected group. They have the different parity. They maintain the parity. They maintain the parity, even parity or odd parity. So we're actually trying to guarantee they will give us a even parity. So using that kind of principle, because that's how we generate our 7 bits code word. So using that principle, we could actually detect the error and correct the error. So how can we do that? So first of all, we will take the B1, B3, B5, B7. So that's the first and the third, the fifth, the seventh. So the 1357 bit location, and do a XOR of them. Do XOR of them. And that will give us a number one. And then we will do the XOR using 2367. And that will give us another number 1. Okay? So, and then we will do the last XOR of the last group, which is 4567. And that gives us a number 0. that give us a number 0. So actually, if there's no mistake, then you will always get 0. If there's no mistake, then you will always get 0. However, this is what we got, right? This is what we got. So no matter how, we'll just do this kind of check. And then we could, this kind of check, the check result actually tells us where the arrow is, because the binary sequence of the check result is 0, 1, 1. Is 0, 1, 1. So we call this C2, C1, C3, C3, C2, C1. So the binary sequence is 0, 1, 1. The decimal number, the decimal value of 0, 1, 1 is actually 3. The decimal value of 0, 1, 1 is actually 3. So 3 tell us then B3 is actually wrong. So it's kind of like playing on magic, right? So actually, if you do not have any arrow, then you always get a 0 for your check, equation, for a check equation. But if you got an arrow, then you will have a value of, you will have a different value. And you could check the value, the decimal value of your B3, B2, B1, C3, C2, C1. So by checking the decimal value of C3, C2, C1, then we could tell the location of the arrow. And if I know B2 is wrong, how to correct it? So if B3 is wrong, if I know B3 is wrong, how to correct? By simply flip it. Because if it is wrong, right now it is 1, then I can simply change it to be 0. If it is a 0 and you know it is wrong, then you could simply flip it to 1, right? So the correction process is super easy. You could just flip that bit. But finding the location of that bit is actually harder, right? So this is the arrow detection, 74 Hamming code arrow detection. So let me give you one more example. So suppose we are still using this example. Suppose the bit sequence we have received is 100. Let's make the first bit to be wrong. So originally it should be 1001 011, 1001 011. So the message should be 1001 011, right, from B7 to B1. However, suppose this bit is wrong. Suppose I got an arrow on the first bit location. Then what we get should be 1001010. This is what the receiver got, and the receiver does not know. Where is the error, or if there is an error or not. So all the receiver need to do is C1, C2, C3. Remember that. And the C1 equals the XOR of what? B1, B3, 1, 3, 5, 7, 1, 3, 5, 7, 1, 3, 5, 7, 1, 3, 5, 7, right? So if I took B1, B3, 1, 3, 5, 7, so that will be the XOR of 1, 3, 0, 1, 2, 3, 0, 5, 7, 5, 7, 0, 1, right? And then the second, so let me get this done. 2, 3, 6, 7. And this is 4, 5, 6, 7. So this is XOR of 2, 3, 2, 3, 0, 1, 6, 7, 0, 1. And this is XOR of 4, 5, 6, 7, 4, 5, 6, 7. So the XOR of this is actually what? right? So by doing the XOR of the different bit group, then we could actually generate the C1, C2, C3, and the decimal value of the C1, C2, C3 is actually 001, is actually decimal 1, is actually decimal 1. So that actually tells us B1 was wrong, So the location of the arrow is B1. The location of the arrow is B1. And of course, how can we correct it? By flip B1 to 0. Yeah, by flip B1 to 0, because currently it is 1, and then we could, currently it is 0, so we could flip it to 1, and then we'll be able to correct the error. So this is how we use the 7-4 Hamming code. And you may have a question that you always try 1 bit is wrong. Suppose 2 bit is wrong. Are you able to detect it? Are you able to correct them? And how about 3 bits are wrong? So this is not required, but I would like to mention that. So for certain bit, every code, error detection, error correction code has its ability. So for 7-4 Hamming code, we are only able to correct 1 single bit error. We should be able to detect 2 bits error, but we are not able to correct 2 bits error. And if multiple bits are wrong, we're not always able to detect that. We're not always able to detect that, right? So because we only spend 3 extra bits, and our ability to correct the error is for 1 single bit error. And luckily, in reality, so within a few bits, you're not really likely to have multiple bits to be wrong at the same time, right? So if you send every 4 bits and there will be 1 bit wrong, then your error rate is actually 25%, which is horrible, right? So if I send you a message and every 4 bits there is a 1 bit mistake in it, think about that, how horrible your communication is, and how poor the communication channel is. So how noisy it is, right? So if you have a super noisy communication channel, and that may happen. But in reality, we do not have that kind of bad communication channel. So probably within 1,000 bits or within hundreds bits, and there may be a few bits error, but you do not always using that kind of communication channel that every few bits there is a mistake in it, right? So that's horrible. All right, so this is all we need to cover for error detection and error correction. So we basically covered one typical error detection code, which is parity check, and we covered one typical error correction code, which is the 7-4 Hamming code. So I will go through the quiz 3 in the next video.